Lab 6, before we move on to final project, is going to be the analog to digital converter, or ADC lab. So the required hardware is a little bit more than our Lab 5. We need a STM32F303K8 Nucleo board, USB micro cable that has a data input. So that is standard. We're also going to need a breadboard. We're going to need 3 jumper wires and a potentiometer, or in Analog Discovery 2. Here though, we use the potentiometer, and we're going to come back to this in a second. So we have required software, that's STM32 IDE and MOBA Xterm. If we went through Lab 5, that material is going to be there. The download link for MOBA Xterm will be in the description below the like button, and the video for the previous lab will be in the playlist below the like button. We also have waveforms, but if we're going to use a potentiometer, this is not required. We have a prerequisite lab, and now we're going to go over some background. If you want the actual, just going over the very end with the procedure part, you can skip to the timestamp that I'm going to have on the screen right now. So now we're going to look at background. Analog to digital converters are a way we can convert analog, which is continuous data, to digital or discrete data. The way this is accomplished is through a method called quantization. Quantization is the process of mapping input values from large sets to output values in a smaller set, usually a finite number. This process is usually accomplished by truncating or rounding our values, so going from like a float to an integer. And we see this here, where it looks like a square wave, but we're making it into a sine wave. This is an example of 3-bit resolution with 8-bit level quantization. There are a number of different analog to digital converters, ADC architectures, and the one commonly used by STM32s are successive approximation registers, or SAR ADCs. The successive approximation algorithm computes the voltage of the input signal by comparing it with one generated by the internal DAC, or DAC. This is a fraction of our Vref voltage. This is the reference voltage. If the input signal is higher than the internal reference voltage, then this is further increased until the input signal is lower. The STM32 boards have many different conversion modes that can be set up. For this lab, we're going to examine 3 main types. We have single conversion mode, continuous, and injected conversion mode. It's important to note that each of these conversion modes also have a single and multi-channel configuration. So if the ADC needs to use multiple inputs and convert the voltage, we can do that here. Also, there are more conventional settings such as dual modules, but we're not going to go over that in this lab. So single channel mode. In this mode, our ADC does a single conversion, a single sample of a single channel, and stops when the conversion is finished. So we're going to look at our figure 2 below. We have start, our channel, and then stop. This is an example of a single channel. This mode is best utilized when you only need a single sample once or very rarely. For example, this mode can be used for the measurement of a voltage level of an external sensor to acquire the ambient temperature. A multi-channel scan is the following. This mode, also called multi-channel, we can see we have 2 channels. They're different, channel X, channel Y, and then we start and stop. This mode is the multi-channel again, single mode in some ST documents. It's used to convert some channels successfully in an independent mode. Using Rinks, you could use this ADC mode to configure any sequence of up to 16 channels successfully with different sampling times and in custom orders. We can, for example, carry out the sequence shown in figure 7. In this way, we do not have to stop the ADC during the conversion process in order to reconfigure the next channel with a different sampling time. This mode saves us additional CPU load and heavy software development. Scan conversions are carried out in the MA mode 4, and this is our multi-channel scan. This mode can be utilized when we need to find the initial parameters of multiple analog sensors to operate our device. For example, this mode can be used when starting a system depending on some parameters like knowing the coordinates of the arm's tip in a manipulator arm system. So in this case, we have to read the position of each articulation in the manipulator arm system at power on to determine the coordinates of the tip. This mode can be used to make single measurements or multiple signal levels, or of multiple signal levels, which is voltage, pressure, temperature, and etc. And then with this, we decide if the system can be started or not in order to protect the people and equipment. So like how batteries need a certain operating temperature, so if a machine has a battery, a certain operating temperature, the environment, it might need to heat up or cool down, if it's getting enough power, or if we need pressure to go along with it. Next, we have continuous conversion mode. So far, we've looked at single channel, we've looked at multi-channel, and then we're looking at continuous conversion. This is like a forever loop. We don't have a stop here. This mode converts a single channel continuously in regular channel conversions. The continuous mode allows the ADC to work in the background. So we have a start, a channel, and that's it. This mode can be utilized when we have continuous monitor analog values of a given pin. For example, this ADC mode can be implemented to monitor a battery voltage, the measurement and regulation of an oven temperature using a PID, and etc. We have a multi-channel scan, and this is like this one, but we are doing multiple. This mode can convert some channels successfully with the ADC in independent mode. Using ranks, we can configure any sequence of up to 16 channels successfully, with different sampling times and different orders. This mode is similar to the multi-channel scan, single conversion mode, except that it does not stop converting after the last channel of sequence, but it restarts the conversion sequence from the first channel and continues indefinitely. So again, the mode is similar to multi-channel scan. It's a single conversion mode, except it does not stop converting after our last channel sequence, and it's just going to restart this from the first channel, and it's going to continue indefinitely. Like what I said about the continuous looping here, we're just going to keep going. This mode can be used to monitor multiple voltages. For example, this mode can be used to monitor multiple voltages and temperatures in a multiple battery charger. The voltage and temperature of each battery are read during the charging process. When the voltage or the temperature reaches the maximum level, the corresponding battery should be disconnected from the charger. So like a smart battery that's able to monitor itself. Now we have injected conversion mode. This mode is intended for us to use when conversion is triggered by an external event or by software. The injected group has priority over the regular channel group. It interrupts our conversion of the current channel in the regular channel group. For example, this mode can be used to synchronize the conversion of channels to an event. So we have channel 0, channel 1. We have our conversion sequence, which is suspended, which is part of the injected trigger. We have our injected sequence and conversion sequence resumed. So for this example, this mode can be synchronized the conversion of channels to an event. It is interested in motor control applications where transistor switching generates noise and it impacts ADC measurements and results in wrong conversions. Using a timer, the injected conversion mode can thus be implemented to delay the ADC measurements to after the transistor switching. We have our ADC resolution and conversion speed. An important thing to know about the ATM32 ADC is that it is impossible to perform faster conversions by reducing the ADC resolution. The sampling time is defined by a fixed number of cycles, this is usually 3, plus a variable number of cycles depending the AD resolution. The minimum conversion time for each resolution is then as follows. So we have 12 bits, and we have the 3 plus about 12. This is equal to about 15 ADC clock cycles. And then we have the same thing with this 13. 8 bits is about 3 plus 8. So again, we have our fixed number of cycles, 3, and then we have the bit number, and we add them together to get our actual cycles. By reducing the resolution, it's possible to increase the number of maximum samples per second, reaching even more than 15 MSPs in some STM32 MCUs. We have some additional models that we're not going to look at. This can be found like polling interrupt in DMA, like how we had in lab 3. So this is our lab procedure. What I'm just going to look at real quick is how we would wire this with our STM32 board. So in the notes, we have this. This is in the lab document in the description below the like button. That's how I set up my board. It's very simple if you just follow this instruction right here. We're going to go through this, we're going to write some code, and then we're going to get some output. So our code is going to look like this. Our output is going to look like this. And so we have, actually, that is not what our output is going to look like. That is from the previous lab, and so let's not look at that. So what we're going to have is this code when we're all done. It's going to look just like this. And then we are going to have this as our output. Now, when we adjust our potentiometer here with like a little screwdriver, we just adjust the knob, these values are going to change up and down. And so that's it for this lab. We would just need to code it and demonstrate that the values change when we adjust our little knob inside of here.